It is worth just recalling that if you have a quadratic that's factorized like this, x take 3, you can expand and simplify and get back to a spot that looks like this, minus 3. And in year 8, you learned this process called expansion. And then in year 9, we would have taught you how to go backwards by factorizing. And some of you will have finally mastered this at about year 11, to factor that. Now, what you guys might be aware of, even though you might not have thought about it explicitly, is you can expand and simplify anything. Given a pair of brackets, you follow some rules and you will expand and simplify it out to get here. However, it's not possible to factorize everything. So there are some endpoints, or some points here, that cannot be factorized back up there. For example, if I give you x squared plus 3, that can't be factorized to get back to there. So there is this incomplete relationship. Everything can be expanded, but not everything can be factorized. And that relationship works with differentiating and integrating. So you can very comfortably differentiate this, and you will know that it goes to 8x plus 3. That drop down we've done for ages. It's called differentiating. Going back has 2 words. The book frustratingly calls it anti-differentiating, which is fairly painful, but it gets the point across. The proper word is integrating. Integrating is this process back, and the same incomplete relationship occurs. You can differentiate everything. You follow those rules, you do it carefully without making a mistake, everything can be differentiated. However, there are some functions you cannot integrate. For example, if you have e to the x squared, you can imagine differentiating that pretty comfortably. 2x e to the x squared, it just comes out. However, that's one of the functions that just can't be integrated. Integrating is also rather mind-bending because there are no rules for it. There's not quotient rule, product rule, chain rule that you follow, put together to get it out. There are some techniques for integrating, and Methods Explorer is one of them. But other than that, it's almost ruleless. And that makes it difficult to follow just the process to do, and you need to hunt it down a little more intuitively. So, some notation. If we say, we often use a capital for the starting one. If you differentiate the capital, you get the small one, and therefore if you start with f of x and integrate it, you get the integrand, or the integral function. It makes a lot more sense when we actually start going into it. So, if we just have x, what I want you to do is imagine that we had some function that we differentiated to get x. So we've differentiated to get here. The question is, where did we come from? How do we get an x out? Nice, that must have come from an x squared. So we're like, okay, if I want to integrate this, it must have come from an x squared. Imagine if I was going to differentiate that to get back here. What's the problem? We're not landing back there exactly. Yeah?
Is the x squared on 2?
Yes, on 2 or a half. If I differentiate this, I get that. Therefore, if I integrate this, I get that. You are doing the reverse of differentiating. And the easy check, and you can do this check every time, the check is differentiate your answer and you should end up back there. Yes?
Couldn't there be a plus sign at the end? Do we just forget about that? Or?
No.
Okay.
On the next page, The internet has a wide variety of memes. It is the most common way to lose a mark stupidly, and probably the most painful way to lose a mark in the entire thing, in the entire course. If you're going to differentiate this, the 2 drops down and cancels out the half and you get the x. However, there is some constant on the end. If I differentiated that, the c would go. So if we're looking at x to start with, looking at how to integrate it, it will have come from a half x squared plus c. And there's always this plus c there that we can imagine that might have been there, it might have been 0, might have been 2, might have been 3, we don't know what it was, but once we differentiate it, get back to the x, it would go. But yeah, well done. So there has to be that plus c. What about x squared? What's the antiderivative of x squared? So if we were to differentiate something and end up at x squared, what would it be? Good. It will have come from an x cubed. That 3 is going to be a problem, so we throw a third out the front, and there's a constant there that we can't see. So we call a third x cubed plus c the antiderivative of x squared. And if we differentiate that, we get back to x squared. Alright? I'm flying through this pretty quickly because these are the easier ones. Where will that come from? An x to the minus 4? Good. It will have come from an x to the negative 3, so x to the minus 4 will have come from x to the negative 3. And then if you differentiate x to the negative 3, it would spew out a minus 3. Yeah? So we need to undo that minus 3 by putting minus a third plus c. More fun with fractions. Where does x to a third come from if we were differentiating?
X to the 4 on 3.
Nice. X to a third will have come from x to the 4 on 3. And if we were to differentiate x to the 4 on 3, what would be thrown out the front?
4 on 3.
Nice. How do we undo a 4 on 3?
3 on 4.
3 on 4. Nice. Because if we multiply 3 on 4 by 4 on 3, we get 12 on 12, we get 1 plus c. Alright, so next page. Here's where we actually start touching on the notation of integration. If we differentiate something to get a function, then the notation we use, and you'll have seen it before because I've accidentally printed out sheets with it on there, the integral of that function with respect to x gets us that original function plus c. And there's always this dx on the end, or if you're working with dt, it'll be time, but dx dt says what you're differentiating with respect to. And then there'll always be a plus c on the end there. So, we would say that the integral of x squared with respect to x is a third x cubed plus c. And that's sort of the notation behind this one here, but that was just rough and quick, and now this is using the formal integral sign. So there are some useful formulas associated here. These first two are very simple, but people tend to forget them, so I think they're probably worth highlighting. If you have a constant in front of a function, the integral of that function is the same as if you effectively factor out a constant and then integrate the function of x. So for example, if I'm looking to integrate 6x squared dx, the integral of that is the same as 6 times the integral of x squared dx, which is then 6 times a third x cubed plus c. Now, here's the slightly tricky thing. Because c could be anything, there's no benefit to us writing this. I mean, it feels like you should, because you know the 6 is going in there and going there. But you would never see that written. Because c represents any constant, me saying 6 times a constant while not wrong, is still encapsulating all the constants. So you would never see that, and it would just be written as C. So we tend to exempt C from some of the normal expanding rules. If we times it by 6, we just say, oh, it's still C. Like, if we times it by -3, it's still C, it's just hanging out there. So it tends to get skipped, and that's why your answers will look a little odd initially. Alrighty, here are, I guess, the basic rules that you're expected to know. And these shouldn't be a surprise given that we've done quite a bit of calculus now. K will have come from a kx, because you can imagine differentiating this, you just get k, therefore you need the c as well. Because if we differentiated that, we would get it here. This one seems trippy, but it's the one that we've been doing. X squared will have come from, so x to the power of 2 will have come from x to the power of 3 over 3. That's that n plus 1, or a third out the front, any n plus c. E to the x, unsurprisingly, has come from an e to the x plus c. Only way to get a 1 on x is with an ln x. And so note that if I was going to integrate 5 on x dx, 5 on x dx, I would factor the 5 out, which is then 5 ln x plus c. So you're completely allowed to factor constants out to help you isolate functions that are useful to you. Cos will have come from sine. Now note, the pluses and minuses effectively reverse here. But you know when you differentiate sine, you get cos. Here, when you